voy a introducir en inglés a nuestro primer participante y lecturer. Now, I will introduce our next lecturer, Dr. Robello Samuel. Is a technology fellow at Halliburton and holds adjunct professor appointments at the University of Houston and University of Southern California. He is regarded as one of the world's most influential contributors to advancement of research and practice in drilling engineering. He is an SPE Distinguished Member and Distinguished Lecturer and the recipient of an SPE International Drilling Engineering Award in 2016, an SPE Gulf Coast Section Drilling Engineering Award in 2013. In addition to publishing more than 200 papers and 14 drilling books, Dr. Samuel holds 62 patents and 45 patent pending applications. He holds a Bachelor of Science and Master of Science, both in Mechanical Engineering, and also a Master of Science and a PhD in Petroleum Engineering. The title of his presentation is Digital Twin and Engineering Analysis for Well Integrity Management. Dr. Samuel, please, you can start your presentation.
Thank you. Thank you for the kind, generous introduction. Good afternoon. And I would like to take you through some of the digital twin that sets the pace for this track. I have been in Houston as a technology fellow with Halliburton last 25 years. And my title is the Digital Twin and Engineering Analysis with reference to Well Integrity Management. When you look at this picture, it tells how the medical industry has transformed. You see the health monitoring. They use digital twin, continuous sensing. Never we want to compromise on the integrity of the body. In other words, integrity of the health. What is driving this? Different technological advancements are driving this. If you take a lot of sensors, devices that are being used, the second one is smarter algorithms, artificial intelligence, data analytics, machine learning. All these things are infused in the health industry. Then faster processing speed, you can see, you can wrap it in your hand and monitor a lot of things. In addition to that, improved visualization on the go, anywhere, anytime. You can see what is happening in your body. In addition to that, the medical science, medical engineering is infusing into this space. Biomechanics of the body. These are all studied more into this. These are all the comprehensive advancement that is pushing the health industry. With the same backdrop, can we do a health monitoring of our well? How does the digital twin is going to act so that we don't want the well integrity to be compromised at any time, whether it is during drilling or during production or abandonment or further, right? So when you look at the landscape, a lot of technologies, the horizontal industries are providing impetus. Science, technology, the way in which we process is completely optimized, connected on the go that we can leverage to find out the well integrity so that it is not compromised. It is not just monitoring at the wrists. We can monitor on the palm of our hands what is happening. What is the well integrity? What is the asset integrity? What is the project integrity? That we can use it. What is the same force driving it? Same, we have now a lot of advanced sensors, IoT devices, IIoT devices at the edge where we can monitor. We're getting hold of the neural network, smarter algorithms. In the morning, we saw video analytics. How do we do that? How do we process it? We have faster processing speed, bandwidth that we can aggregate, not only aggregate, but we can extract information at a much faster pace. Ultimately, we wanted to visualize. We wanted to visualize on the go, anywhere, so that we are never disconnected what is happening from the well. Now, an important point is when the medical industry is advancing on medical sciences, we are also advancing in well engineering space. What is happening downhole? Reservoir space, production space, well intervention. So that all contributing towards the well integrity. So the engineering is an important part in the digital twin. So you can see the wellbore integrity that we need to duplicate before drilling a well. Then casing integrity. If we go beyond the well, we have to see the casing integrity. Then we have to see beyond that what is happening in the annular space. What is the wellhead growth? Annular fluid expansion. Is it causing corrosion? Or is it getting compromised on erosion, corrosion, wear? All these things. Then the cement integrity. You can see we not only from the well, but we are going beyond that. Then junction, if we have multilateral wells with the junctions, we need to maintain the junction integrity. Then top side, the structural integrity. Structural integrity is very important. Now top side, whether it is onshore, offshore, that we need to take into account. Now finally, the data integrity. The data integrity is very much important as we go into the digital twin space. So these are all coupled through three things: engineering, data science, artificial intelligence, machine learning, deep learning, then uncertainty, because we deal with a lot of uncertainties, downhole uncertainties, the profile, well design, the casing wear, all these things are uncertain. So we need to have an uncertainty-based approach to come up with a digital twin. So that will provide a comprehensive analysis of monitoring the health of the well as the medical industry is doing. If you move on to that, we need to have an important thing that is an open platform that we can easily connect to different twins, whether it is on the well drilling side or casing side or cement or production, whatever side. So we can have a connected assets twin that will provide a comprehensive offering to the industry. So you can see from starting bits, real-time data, production, then transforming the data through IoT devices to the space that where we want to visualize it. So embedded E&P data management is important. At the same time, we need to have a cloud native system so that we can stream the data, not only streaming the data, but also we can analyze the data and visualize it. Then we should be able to predict ahead what is going to happen. When is the workover going to happen? What is the health of my well? Not only that, but also the health of my whole asset I need to see. So smarter equipment, real-time connectivity, cloud integration, then big data analytics. It is not just a PowerPoint, right? We have all these technologies, but we need to put it in an open platform that we can plug and play any digital twin. So for that, we need a comprehensive artificial engineering intelligence, AEI, mesh-driven well integrity management system, not just an ordinary dumbed-down well integrity management system, but we need to have hyper-time compression because we have a lot of data coming from different wells, different assets, and we should be extreme convergence. We should do multiple engineering calculations at a faster speed, but we have the technology. Then we use the artificial intelligence that will mesh all the things to have a comprehensive well integrity management system, which will be virtually perfect, but governed by physics and data, not just data, not just physics. It's a hybrid approach that will incorporate physics and data. So the data will handhold where the physics are going down, or the physics will handhold when the data is highly uncertain. So that will be a well-connected, well-integrity management system on the go. So single enterprise platform that we need, it should be flexible, modular, that it should be able to provide an option to select what you want rather than making a rigid platform. Then open source standards, that where we can connect it, any open source connectivity, any databases, not on a rigid scale. Then total cost deployment should be flexible and affordable. How does it work? So now we have the information management foundation where we have several databases like traditional recall, EDM, MDS, data, PDM, Insight. But there are other things from the third party databases, and also you may have unstructured data stored in a database. So it should be available to connect any of these options. Then there should be an integration foundation, service-oriented architecture that we can connect anything, right? Uncertainty. I need a separate uncertainty module that I have more confidence than a third-party uncertainty. That we should be able to do it. And the importance is the engineering. Of course, we know the data quality, we have to do it. Then analytics, the space is so big, right? Then business process engine that you need to structure it and adjust it as and when needed. Then application foundation. So you have a lot of foundation layer in that layer that you can make it to visualizable, whether it is on a mobile device, on a web base, or in a standalone in a local machine. Then finally, the ecosystem foundation, that where all the things are connected through the cloud, the plugins, extensions, of course, the customizable dashboard. So it may look very comprehensive, but the thing is, it should be modular, as I explained, that you should be able to connect whatever I need. So that provides a solution that is not very rigid, but it is more modular. So I can connect any engineering module that it is needed for that. And also you can make it more artificially intelligent, as I presented earlier. So automatically it runs through the calculations to come up with the solutions that is needed. Then it should be holistic. It should be a life cycle management, not just a well, but it should be end-to-end for a particular well, whether it is a particular well or a wellbore or an asset. You should have the basis of design, construction, operational intervention, and abandonment. Then you should relearn. Sometimes you may need to unlearn what you have studied, but you have to take it beyond that. That will provide the reinforcement to the learning system. That provides the digital space well integrity management, which is modular, affordable, and easily deployable. Then you have integrity on the visualization. You have the assessment tools, because we need to assess what is the risk that I am taking, and can I have an estimate that what I need to do in the coming months. How many wells are going to be shut down? How many wells are going to be put on workover operations? These are all important. Now we have a lot of edge devices where we can put it on the wellhead, IoT devices where we can stream data and do the stream data analytics. That will also incorporate some failure models on a asset basis. Then, as I said, we have to move and view what is happening on the go, real time, never offline, connected and see what is happening. I want to see on the palm of my hands through some of the devices. And eventually we have to report. Emerging well integrity opportunities, you see a lot of things are changing tremendously. The horizontal industry is providing the exponential technologies that are growing very fast. You can connect third-party monitoring devices or automations that can be connected to the cloud, and eventually you can easily duplicate what we want. So that, as I said, not only the IoT devices, but also IIoT and the edge computing and the edge devices are helpful in this space. Then the important one is the engineering coupled well integrity. Otherwise, it will become just a dashboard processing data, slicing and dicing the data, but it doesn't provide what is happening, what is the physics behind it, the justification of the failure of the well, and also the predictability of the well using the model. Then, as I said, it is a hybrid approach that physics plus data. Then we use data analytics, artificial intelligence, and machine learning so that we can learn, relearn, reinforcement on the data that will provide more comprehensive analysis. So that makes it very evergreen. The digital twin and the well integrity management, that we can always make it evergreen. That is, always it updates because of the real-time data that are coming in. So we have smart systems, lot of valves, smart wellheads, making it more digitally twinned wellhead, and also the supply chain, how much we need to replace, what are the parts needed so that they never go offline. That is the physical barrier asset. Then we make the well integrity digital twin. Most of the time we make the digital twin and compare it with a physical barrier asset, but here we have a lot of wells that we can use it as a baseline, then digitally twin. Then also you can connect it back to the physical barrier. So we have other devices, AR, VR, IoT devices, interactive devices. We have seen visual analytics, all these things. We can combine it with a well engineering. That will provide the well integrity management. That is the space for engineering and science. So you can clearly see the demarcation. That is the engineering and science. Engineering, what we have done, what it is going to happen. I will give an example. And the science, the data science, machine learning, artificial intelligence in that space. Then the technology, cloud, big data, providing stream analytics, processing of all the data, quality control. That eventually is a combination of this digital well integrity management system. It is not just a well integrity management system. I'll take you through a simple example for this engineering coupled well integrity management system. This is an offshore well. You see a surface liner, then an intermediate casing, and intermediate casing that is 13.5/8 and 7-inch production crossover, then a 5.5-inch production tubing. So now it's a complex casing design which has not cemented all the way, and it has a lot of issues it may come up, right? Wellhead growth, annular expansion, and uncemented portion corrosion. How do we justify and calculate the well integrity management? So we need to have essentially, if you think of the production, 1 year, 1 day, 1 month, 1 year, you can see clearly how it changes. The temperature profile, different now. We see annular A, B, C, and it may be prone to leakage in the coming days. Maybe it is good, as we have seen the health of a body. Then, but it slowly it gets degraded. So if you think of not only on the well side, the top side is also important. The seals that are sealing at the top on the wellhead, it's a subsea well. Now, the temperature, the change in the properties of the mud behind the casing, how it is going to get affected. Not only just looking at the movement of the casing, but also we have to see how the whole composite system is getting affected. You can see here as it is producing 1 day, 1 year, 1 month, and several years, it completely changes. And the displacement is appreciable. That we cannot neglect it. Just getting the data, putting IoT devices on the surface, measuring all these things, not only, it's not going to help, because we need to understand the physics that is going behind this comprehensive well design. Because the data doesn't know the physics. But we have a lot of assumptions when we calculate the temperature profiles and the wellhead growth, annular fluid expansion. But the data will always handhold and suppress some of the uncertainties, and it neutralizes some of the paradoxes which we see in the day-to-day life. So this comprehensive analysis provide a more in-depth analysis of well integrity management, and not just a business practice, but it infuses the underpinning of engineering calculations. With that, I would like to summarize with that. Right now, with all these calculations, we have to have a summary report. What is going to happen? Okay, I do all these calculations, but I want to visualize what is happening in a particular well. Is it giving a signal that it is going to be under workover operation for 2-3 months? Or should I take remedial action so that I can mitigate the downtime? So it adds value. So some of the invisible lost value, then we can recover. And also, I need to see the risk. Can I take the risk of producing the well for another month, but still I can reduce this problem? We can avoid it. So that will give on the bottom of that one the risk graph and the risk index, and also I can see how the asset is performing. One well, probably I can take the risk, but I should not take the risk of 50% well shutdown. So it gives a comprehensive analysis, which we can do it using the digital twin. Finally, in summary, in few concluding thoughts. Before parting, I wanted to emphasize we have to go beyond presenting just a business practice, but we need to have a comprehensive analysis that will be more intelligent. Artificial engineering intelligence, that is hyper compression of data so that we can analyze and derive value out of it. And also end-to-end life cycle integrity. Now we can digitally twin each component, and also we can have a comprehensive digital twin. That will be possible by leveraging the engineering science, what is happening. That will have the physics embedded into the system. Then definitely we have to learn and adjust. The digital twin is evergreen, so it can update as we get more data and update. Then it helps not only monitor the old wells, but also new wells in real time. So now old wells, probably we may not have monitored properly, but still I think we can mitigate as the age of the well As the world ages, definitely we have to have a different approach as opposed to the new worlds, where we have digitally connected, so we can monitor in a better way compared to the old worlds. So the platform, DS WIM, or the artificially intelligent enabled well integrity management, is scalable. And it is flexible, as I explained, that we can plug and play and remove whatever you want. And finally, we can use it and tailor it for our need. That is the system that will be on the edge and in real time. With that, I would like to conclude and thank you for your time. And if you have any question, I'd be happy to answer. Thank you.
Dr. Samuel, thank you very much to be just on time with your presentation. We have no question from the audience, but I found your presentation very interesting. I would like to understand, because this amount of data, you need it's a challenge to have interoperability because you have sensors. These sensors are part of different equipment. These equipment come from different OEMs, suppliers. So you need standards to do this digital twin in a wearable reality. These standards and this interoperability is ready, or it must be developed yet?
That's a good question. This is one of the questions come always. So if we dissect the question, one is the standard, right? We don't have, there are standards introduced, but it didn't go far enough that we can make it a comprehensive analysis. So that we need definitely some standards. It is coming. It's always a difficult proposition because the different OEMs, they have different standards. Like PPDM, all these things are coming up with a comprehensive standardization of the data so that anybody can use it. That is an issue, definitely. Then interoperability. That's why I was telling on the open platform where you structure that API or accessibility in such a way that anybody can tune and connect it to this platform. Now, the third one is, this is always a problem, both the questions, the interoperability and the standard. So now, are we going to achieve? Probably not. So how do we circumvent this issue? So do we need a standard? Do we need a uniform interoperability one? So all we provide a platform that anybody can plug and play as long as it passes the data as it is needed, then we are okay, right? The question is probably we may not need a standard, but we need a comprehensive platform where anybody can plug and play as per the platform provider who can connect it. So it can be a common platform, it can be a common architecture or a common framework where you can plug and play. That's why I was providing different layers that is modular. So I don't need that level of data from a particular vendor. So you just pipeline whatever is needed and use it. So the question is yes and no, right? It is a complex issue. It is not plaguing oil and gas. It is in other industry also. The same issue in the medical industry, but they are very open in sharing the data, but at the same time providing security around the data.
Okay. Well, thank you very much. We are on time. I guess you can answer at least one other question. Mr. Juan Carlos González is asking a question. he says, is it possible to take in consideration eventual localized corrosion phenomena in tubing or casing?
Yes, that is one of the biggest problems, the corrosion, right? It's now when you look at some of the old wells, all these wells are leaking, either corrosion in the tubing or corrosion in the casing. Tubing is easy to change, but the casing, how do we do that? So, but at least we can monitor with the support of software, not only on the software, but also on the hardware. Finding out what is happening, at least we can mitigate before going into colossal wreck.
Okay, well, Doctor, we have no more time. There is another question, couple of questions, but we have no more time, so I have to continue with the other presentations. We want to thank you very much for your presentation and your participation in this Congress.